So last time we studied ring of integers of biquadratic extensions in some cases, and we are going to finish the last case today. So let me remind you what we did. Change the color. Okay, so a biquadratic field is a field of the form q square root of m square root of n, where m and n are distinct square free integers, m n distinct square free integers. They are distinct, but they need not be co-prime, and so what we did was we put k as m times n by GCD of mn square. Okay, so k is a biquadratic extension of q with Galois group Z mod 2 cross Z mod 2. So it's good to describe this in a diagram like this. So you have q and then you have k here, and there are three proper intermediate extensions. So you have q square root of n here, q square root of m here, and the third field is of course this k that we define in terms of m and n. Okay, and so we looked at various cases for computing rings of integers. So we looked at various cases. Case 1 was when m is congruent to 3 mod 4 and n and k are both congruent to 2 mod 4. Right. In this case, we proved that OK has z basis given by 1 square root of m square root of n and square root of n plus square root of k by 2. Okay. And then here is an exercise that you can do. Is discriminant in this case turns out to be 64 m n times k. Okay. Now case 2 that we considered was m is congruent to 1 mod 4 and n is congruent to k is congruent to 2 or 3 mod 4. Okay. Again, in this case we proved that OK has z basis given as follows. It's given by 1 plus square root of m by 2 square root of n square root of n plus square root of k by 2, and again you can take as an exercise that discriminant in this case is 16 m n k. Okay. And I should remark here, although it should be clear, m n and k, what they are modulo 4 is not independent of each other, because there is a relation. K is defined in terms of m and n. K is m n divided by GCD of m n square. Okay, and a square is always 0 or 4 0 or 1 mod 4, and so if m and n are both 2 mod 4, k will be you will have to divide by 4, etc. So there are these conditions. So so case 3 is what we are going to look at today. Case 3 is m is congruent to n is congruent to k is congruent to 1 mod 4, right. And here is another exercise. So cases 1, 2 and 3 cover all possible cases. Okay. As I said, you can't have any combination for m, n and k. There is some relation between them, and so you can show that by permuting m, n and k around, these cover all the cases that there are. Okay. And what did we do? What did we use last time? So what did we use? We use that alpha belongs to OK if and only if norm from k to q square root of m of alpha belongs to O q square root of m, and trace from k to q square root of m of alpha belongs to the ring of integers again, right. And so we can use, I mean, there is nothing special about m here, we can use it for m, n and k, all of them. So this is the kind of thing that we used. Now let us come back to this case. So I am going to make a following claim. If alpha, which is a0 plus b0 square root of m plus c0 square root of n plus d0 square root of k, this is the notation that we used last time. So a0, b0, c0 and d0, these are in q. Then in fact a0, b0, c0 and d0, they belong to 1 by 4 z. So the denominator is at most a divisor of 4, and if a0 is a by 4, b0 is b by 4, c0 is c by 4, d0 is d by 4, then a is congruent to b, is congruent to c, is congruent to d, is mod 2. Mod 2. So a, b, c, d are integers, and my claim is that if alpha is of this form, then this is this is the relation between the coefficients. So how do I prove this again? Let us see. So so what we know is that the ring of integers, so as m is congruent to n is congruent to k is congruent to 1 mod 4 O q square root of m, this is z 1 plus square root of m by 2, and similarly for q square root of n and q square root of k, right. Okay. So what I am going to do next is I am going to look at trace, as we did last time, of this alpha, and this of course turns out to be 2 times a0 plus 2 times b0 square root of m, which belongs to z 1 plus square root of m by 2, right. So what this means is that 2 times a0 plus 2 times b0 square root of m, this is some x plus y 1 plus square root of m by 2, which I can rewrite as x plus y by 2 plus y by 2 into square root of m, right. And x and y are integers, x and y, they are integers. This means that 2 times a0 and 2 times b0, they belong to half integers, which means that a0 and b0 belong to 1 by 4 z, right. Okay. Furthermore, I mean, you have a more concrete relation. This is this is 2x plus y by 4, and b0 is y by 4, right. And so if I write a0 as a by 4 and b0 as b by 4, then so if this holds, then a is 2x plus y and b is y, right, which means that a and b are congruent mod 2. So hence a is congruent to b mod 2, right. And then we can do the same thing. So similarly by considering trace from k to q square root of n of alpha, we get a0 and c0, they are in 1 by 4 z. I mean, we do not need to consider a0 again. Okay, so let me not do that. Is in 1 by 4 z, and if c0 is c by 4, then a is congruent to c mod 2, right, as before. And by considering trace from k to q square root of k of alpha, we get d0 is in 1 by 4 z, and if d0 is d by 4, then a is congruent to d mod 2, right. So we have proved the claim. Okay, so hence we get the claim, hence we get the claim that we made. Okay. So now the next claim is the following, right. So what we have is alpha which is in OK, this is of the form a plus b square root of m plus c square root of n plus d square root of k by 4. A, b, c, d, they are integers and they have the same parity. Mod 2. Okay, so either all of them are even or all of them are odd. Right. Okay, so next what we do, next claim is that alpha can be written as r plus s square root of m plus t square root of n by 2 plus some integer multiple u times 1 plus square root of m by 2 into 1 plus square root of n by 2. Okay. So, r, s and t, these are in z, and r plus s plus t is congruent to 0 mod 2, right, and u is also in z. Okay. All right. So, I will prove the claim in a moment, or at least give you some idea of how to prove the claim. But let me, so if we assume the claim, so what does claim give? So, claim implies that OK has z basis 1 plus square root of m by 2, 1 plus square root of n by 2, and 1 plus square root of m by 2 times 1 plus square root of n by 2. Okay. So, yeah, it should be clear that all these are algebraic integers, because 1 plus square root of m by 2 is an algebraic integer already in q square root of m. Similarly, 1 plus, sorry, this should be k and not, yeah, everywhere it should be, sorry, there is a typo here, this should be k, square root of k, square root of k. Yeah, so all of these are algebraic integers. So it is clear that this is contained in the ring of integers of OK, and I am saying that that is a basis. So, why does claim give that? Well, you see the last element is already here, u times something. So, you just need to notice that that r plus s square root of m plus t square root of n by 2, it can be written in terms of 1 plus some multiple of 1 plus square root of m by 2 and some multiple of 1 plus square root of n by 2. And how do you do that? Yeah, so let me say how this is done. So, we need to show that r plus s square root of m plus t square root of n by 2 r plus s plus t congruent to 0 mod 2 can be written as a z linear combination of 1 and 1 plus square root of m by 2 and 1 plus square root of n by 2. And so, you do not really have much choice. What you do is you take r plus s square root of m plus s minus s plus t square root of n plus t minus t divided by 2. And so, you can write this as r minus s minus t by 2 plus s times 1 plus square root of m by 2 plus t times 1 plus square root of n by 2. And now, this thing you can just rewrite as r plus s plus t by 2, which is even minus s minus t plus. So, this is an integer, and then you just have 1 plus square root of m by 2 plus t times 1 plus square root of n by 2. Okay. All right. So, that is what this is, and so hence the claim shows you that this is the this thing is the is a z basis of OK. All right. So, we need to prove the claim. So, proof of the claim. Okay. Right. So, what is 1 plus square root of m by 2 into 1 plus square root of k by 2? This thing is 1 by 4 times 1 plus square root of m plus square root of k plus square root of m k. Right. And so, what is square root of m times k? Right. So, square root of m times k, this is some integer multiple of n for some a in z. Okay. That is how things are kind of set up. So, all right. So, what do we? Yeah, now that I think about it, it is probably better to do things where m and 1 plus square root of m by 2 and 1 plus square root of n by 2. It may be better to do things that way, but anyway, let us kind of do it this way. Then what do we have? Right. Okay. So, maybe I should not write a here, I will write some other letter v. Okay. Okay. So, alpha is a plus b square root of m plus c square root of n plus d square root of k by 4. And as I said before, a, b, c, d are integers. A is congruent to b, is congruent to c, is congruent to d mod 2. Okay, these are the kind of calculations one should do oneself. The reason I am showing you all these calculations, all these cases is so that you get familiar with the kind of ideas that go into proving such things. You may not necessarily use the exact same thing ever, but at least you know what kind of ideas should go into it. Okay. All right. So, now what I am going to try to do is the following. So, I want to put my alpha in two different forms. Right. I want to right. Okay. I want to write my alpha as a plus b square root of m plus c square root of n minus d square root of m minus d square root of n by 4, and then since I have subtracted this, I should also add these somewhere. So, I should have plus yeah, maybe one more term, sorry, not just this one, but minus d, and then I should add all those terms. So, I should get d 1 plus square root of m plus square root of n plus square root of k by 4, right. So, this is not quite what we want, okay, because we have v times square root of n there and not yeah. So, we have some multiple of that. So, what I am going to do again is sort of make things more complicated and write it as follows. So, plus b minus d square root of m plus c minus d square root of n, and then this a should be just a minus d. Okay. But now here I want d times v square root of n, right. So, I am going to write here yeah. So, I am just going to do d plus 1 plus square root of m plus v times square root of n plus square root of k by 4. So, what have I done? I have added v minus 1 times d as an extra thing here. So, I am going to subtract that thing from this. So, d into v minus 1 times square root of n by 4. Right. So, it all looks very complicated right now, but I can assure you that it will simplify in a second. B minus d square root of m plus what is this thing? I have square root of n common and then minus d common. So, this becomes c minus dv square root of n by 4. And then this thing is d times 1 plus square root of m by 2 into 1 plus square root of k by 2, right. So, I want to forget about this. Why should such doing something so ad hoc work? Because it is a z basis. So, there is a unique way of writing everything in terms of such a z basis, right. So, I can ignore this for the moment and I just concentrate on this. So, I just concentrate on this particular part, which is yeah. So, let me write that on the next page. So, consider a minus d plus C minus D, I hope I am getting this right, B minus D, not, this should be B minus D square root of M plus C minus dV square root of N by 4. And now you see that A minus D is even, A minus D and B minus D are even, right. What about what about V? V is necessarily odd, right. So, this is, maybe you can take this as exercise. This is because M is congruent to N is congruent to K is congruent to 1 mod 4. So, you see how V comes about, and it has to be odd, which means that C minus dV is also 0 mod 2, right. So, either C and D are both even, in which case this is true, or C and D are both odd, and you are multiplying an odd number D by another odd number V, and so dV is also odd, and you get what you want, right. So, you can write this as, so A minus D you can write as 2 times R, B minus D you can write as 2 times S, and C minus dV you can write as 2 times T, right. So, firstly what you get is this thing becomes R plus S square root of M plus T square root of N by 2, and what is R plus S plus T? This is well, at least 2 times this is A minus D plus B minus D plus C minus dV, which you can rewrite as A plus B plus C minus D times V plus 2, right. Which you can rewrite as A plus B plus C plus D minus D times V plus 3, right. And now what you can what you notice is that so again, just the way things are set up, you can show that this thing is divisible by 4. Okay, so maybe you can take this as an exercise. You prove that A plus B plus C plus D minus D times V plus 3 is congruent to 0 mod 4. Okay, and that will prove for you that R, so then R plus S plus T is congruent to 0 mod 2. Okay. All right. So to do this exercise, you may have to take a few cases on what. So, you know that A, B, C and D, they have the same parity, right, but you can consider them modulo 4 and then take various cases and show that you get what you want. Plus you should also prove that you should have something about V as well. So, I think V is 1 mod 4 all the time. Okay. So, that is how you prove the last remaining case, and here is an exercise. So, in case 3, the discriminant is equal to M times N times K. Okay. All right. So, this computation of discriminant, by the way, is not an easy exercise in these 3 cases, but you should try to do it. That is other exercises are all easy. Okay. So, today we finished computing rings of integers of biquadratic fields. Next time I will say a word about units in biquadratic fields, at least in certain cases. and we will also revisit units in real quadratic fields. So, we in an earlier lecture we saw how to get units in a real quadratic field, in fact infinitely many units, but that was only those with norm 1, and today we are going to try to see in the next lecture we will try to see all units in a real quadratic field. So, also with norm -1. Okay, thank you.